Tomorrow, 99.999% of humanity disappears. Only a few people are left alive. Would that be enough? Or is humanity already extinct, just walking around and not knowing it yet? The answer isn't a nice round number everyone agrees on. It's a genuine, ongoing argument between scientists, and the range they've come up with is almost absurdly wide, anywhere from under 100 people to well over 10,000, depending entirely on which question you're actually asking. Compared to most other species, humans have strikingly low genetic diversity, less variation across all 8 billion of us alive today than inside a single troop of 50 wild chimpanzees. For years, the leading explanation was the Toba catastrophe theory, the idea that a supervolcanic eruption in Sumatra, roughly 74,000 years ago, crashed the global human population down to as few as 10,000 people. It made for a dramatic story, and for a long time it was treated as settled fact. More recent archaeological evidence, stone tools found both above and below Toba's ash layer in India, and a detailed 2025 review directly challenging the theory, has cast serious doubt on it. Whatever actually caused it, though, the low genetic diversity itself is real. Our ancient ancestors, at some point, really were down to a surprisingly small number of people. Which brings us to the real question. Exactly how many people would you need, starting from scratch, for the species to keep going? Conservation biologists have a rough rule of thumb for this, developed for endangered species long before anyone applied it to humans. It's called the 50 to 500 rule. Roughly 50 individuals to avoid immediate inbreeding problems, and roughly 500 to maintain enough genetic variation to keep adapting over generations. It's a widely used starting benchmark, though it doesn't apply equally well across every species. When researchers tried applying this specifically to humans, the estimates scattered in every direction. On the small end, astrophysicist Frédéric Marin and physicist Camille Belloufi at the University of Strasbourg in France ran detailed computer simulations calculating the minimum crew needed for a multi-generational voyage to another star system, using custom software that modeled centuries of births, deaths, and pairing across simulated generations. Their conclusion was strikingly small. A minimum of 98 people, carefully managed, could sustain a genetically healthy population for a journey lasting over 6,000 years. Drop below that, their simulations showed, and the odds of success collapsed fast. A crew of just 32 had essentially zero chance of avoiding inbreeding entirely. Anthropologist Cameron Smith looked at the exact same problem in 2014 and landed somewhere completely different: 14,000 people. His reasoning wasn't purely genetic. He based his number on the actual demographics of real human societies that survived and thrived in isolation, including Polynesian voyaging populations that successfully settled remote Pacific islands. Even small, hardy hunter-gatherer societies typically survive in groups of around 100, but crucially, they've always been able to interact and occasionally interbreed with neighboring groups. A truly isolated population, cut off completely with no outside contact ever, would need vastly more people to avoid the same genetic problems long-term. 14,000, in Smith's view, was a conservative estimate if the goal was centuries of real survival rather than just avoiding immediate genetic collapse. Other researchers land somewhere in the middle of that gap. A widely cited cross-species survey found a median minimum viable population across many vertebrates of just over 4,000 individuals. Various geneticists studying mammals broadly have suggested numbers between 500 and 5,000, depending heavily on the assumptions built into each model. That massive gap between 98 and 14,000 isn't really a disagreement about biology. It's a disagreement about the actual question being asked. Marin and Belloufi's 98 is a pure genetics answer, the bare minimum to avoid catastrophic inbreeding in a tightly controlled, carefully managed scenario. Smith's 14,000 is a real-world survival answer, enough people not just to avoid genetic collapse, but to actually build and sustain a functioning society, with enough specialists, enough resilience against disease or disaster, and enough structure to raise children successfully across generations without everything falling apart the moment something goes wrong. That distinction matters more than the raw numbers themselves. Surviving genetically and surviving as an actual civilization turn out to be two almost completely different problems layered on top of each other. A population of 98 people might theoretically avoid inbreeding for a while. It would almost certainly struggle to maintain doctors, engineers, teachers, and farmers, especially the moment anything went wrong: an illness, an accident, a single bad harvest. So the honest answer to how many humans it would take to restart humanity depends entirely on what kind of restart you're imagining. Enough people to avoid immediate genetic collapse is a number small enough to fit in a single school gymnasium. Enough people to rebuild something resembling the world we actually live in, with medicine, infrastructure, and knowledge passed down intact, is a number closer to a small city. The real bottleneck was never just our DNA. It was whether enough people remained to pass on everything that made us human. Civilizations aren't rebuilt by genetics alone. They're rebuilt by people who remember how to build them.